Today we are going to discuss the effect of a frameshift mutation on a protein sequence. Imagine that you are at a sporting event and see a group of people cheering on their team. They each have a shirt on that has a letter spelling out a phrase. In this case, go team. Now imagine that one of the participants leaves. The phrase no longer says go team and does not make sense in the context of the event. This is an example of a deletion. If the opposite happens and another friend joins the group with a random letter, then the phrase will also not make sense. This is an example of an insertion. The same thing happens in protein sequences. As you can see, the mutant strand is no longer the same as the normal strand, indicating an addition or deletion. To determine where the frameshift mutation occurred and how it affects the protein, it is important to list all possible codons for each protein in this sequence. As you can see, some of the proteins have one option, while others have many options. It is also important to do the same thing for the mutant sequence. Once all of the possible codons are listed, we are able to compare the two strands and identify the mutation. In the mutant strand, there is an addition of an A. In the sports fan example, this would be the same as someone in a shirt with a random letter joining the cheering section. Due to this insertion, the reading frame will be shifted, meaning that every codon and protein following the mutation will be affected. The process of determining the mRNA codon sequences requires comparing the two strands to see where the codons match up. The proteins before the addition will not be affected and thus will be the same. As you can see, the codons of the normal and mutant strands no longer line up, but are off by one. This shift changes the 3 amino acids that go together to form a specific codon. By doing this, we are able to see which of the possibilities is the correct codon sequence. Here are the normal and mutant mRNA sequences. As you can see, we are not able to determine all of the codons for the normal sequence. This is due to the fact that the mutant strand hits a stop codon and ends before the final codons of the normal sequence. There is no way to compare and determine the codons, meaning that to our knowledge, all of the options are still possible. This process shows how one addition or deletion can change an entire protein sequence. This new protein could have a brand new function or it could have no function at all. Both of these options could be detrimental effects on the cell or organism.